Our visible universe is a grand illusion. The stars and galaxies we admire are just a tiny fraction of what truly exists. An immense, unseen structure, a dark skeleton, dictates the shape and fate of everything. By the end of this journey, you will understand the invisible forces that hold our reality together. We will uncover how scientists map a ghostly cosmic web and why most of the universe is missing from our senses. What do you believe is truly real? Every great structure relies on a hidden framework for its strength. A skyscraper is not held up by its glass facade, but by a steel skeleton within. Our universe operates on the same principle. The glittering tapestry of galaxies we see is merely the decorative surface, while the true support comes from an invisible cosmic web. This is the dark frontier, the unseen skeleton of everything. For nearly a century, astronomers have known something was missing. In the 1930s, a sharp-witted scientist named Fritz Zwicky was studying a distant cluster of galaxies. He noticed something bizarre. The galaxies were moving so fast that the cluster's gravity, based on all the visible stars and gas, should not have been able to hold them together. The entire group should have flown apart. Zwicky concluded there must be some unseen matter providing the extra gravitational glue. He called it Dunkel Materie, dark matter. For decades, this was a fringe idea, but the evidence became undeniable. We see stars at the edges of spiral galaxies whirling around at speeds that defy logic. If only the visible matter were present, those outer stars should be flung off into the void like mud spinning off a wet bicycle tire. They are not. Something invisible with immense gravity is holding them in place. This ghostly grip extends to the oldest light in the universe, the cosmic microwave background. The subtle patterns in this afterglow of the Big Bang are a cosmic blueprint, and they can only be explained by the presence of a vast amount of dark matter. So we know this skeleton exists, we feel its gravitational pull, but what is it actually made of? We have no idea. It does not emit, absorb, or reflect any light. It simply does not interact with the electromagnetic force, the very thing that allows our eyes and telescopes to see anything at all. It is a substance fundamentally alien to our everyday experience, yet it makes up about 85% of all the matter in the cosmos. This leaves us with a profound puzzle. How do you map a shadow? How do you trace the outline of a ghost? The answer lies not in looking for the skeleton itself, but in observing how it bends the world around it. The path to mapping the invisible begins with a simple, profound truth. Gravity bends light. Picture a massive galaxy cluster floating in the void. Its immense gravitational field, dominated by the unseen dark matter, warps the fabric of space around it, creating a cosmic lens. When light from a more distant background galaxy travels toward us, it must pass through this warped space. The light does not travel in a straight line. It bends just as a straw appears bent in a glass of water. This phenomenon is called gravitational lensing, and it is our most powerful tool for seeing the unseeable. We observe two primary types of this cosmic illusion. Strong gravitational lensing creates breathtaking arcs and rings of light, like a funhouse mirror reflecting entire galaxies. The Hubble Space Telescope has captured stunning images of these Einstein rings, where a distant galaxy is smeared into a perfect circle around a closer cluster. These are the undeniable, dramatic signatures of immense hidden mass, but strong lensing is relatively rare. To map the broader, fainter distribution of the dark cosmic web, scientists rely on weak gravitational lensing. Here, the distortions are far more subtle. Instead of beautiful arcs, distant galaxies appear only slightly stretched and sheared, as if viewed through a flawed pane of glass. By meticulously measuring the shapes of millions of these faint galaxies, astronomers can detect this coherent warping. It is a statistical ghost, a pattern that only emerges from analyzing vast datasets. This painstaking work allows researchers to translate tiny distortions into a detailed map of the dark matter's distribution, revealing the massive, invisible skeleton of the cluster. This entire endeavor stands on the shoulders of pioneers like Vera Rubin. Her painstaking measurements of galaxy rotation curves in the 1970s provided the first robust evidence that something was gravitationally gripping the stars. She did not set out to discover dark matter, but to understand why galaxies did not fly apart. Her work shifted the paradigm, forcing science to accept that most of the universe's matter was missing from our view. Gravitational lensing is the direct descendant of that revelation. It takes the ghostly grip Rubin identified and uses it to trace the outline of the ghost itself. Every distorted galaxy we see is a footprint in the sand, a sign that something massive just passed through. These are not just optical curiosities. They are the signposts guiding us deeper into the dark frontier. But what if we could hear this invisible structure too? What if the silent skeleton of the cosmos creates ripples we can actually listen for? That ancient light, the cosmic microwave background, is more than a fading echo. It is the universe's first baby picture, taken when it was a mere 380,000 years old. This afterglow is not perfectly uniform. If you could see it with the right eyes, you would notice a mottled pattern of incredibly slight temperature differences, patches that are just millionths of a degree warmer or cooler than their surroundings. These tiny anisotropies, as scientists call them, are the frozen seeds of all structure. The slightly denser, hotter spots are where gravity would eventually get to work, pulling in dark matter to form the first strands of the cosmic web. Space missions like Planck and the Wilkinson Microwave Anisotropy Probe, or WMAP, were designed to be the ultimate cosmic photographers. They mapped this faint glow across the entire sky with breathtaking precision, creating a detailed chart of those primordial hot and cold spots. Reading this chart is like decoding the universe's DNA. The specific size and distribution of these patterns are a direct record of the ingredients present in the cosmic infant. They tell us with remarkable certainty the exact recipe of the cosmos. Ordinary matter, the stuff of stars and planets, makes up only about 5%. Dark matter constitutes about 27%, and the remainder, a whopping 68%, is the mysterious force we call dark energy. Cosmologists often describe the cosmic microwave background as the single most important dataset we have. One leading scientist remarked that it places the tightest constraints on our models of the universe, acting as a strict anchor for our theories. It confirms that the dark matter skeleton was already in place, providing the gravitational scaffolding onto which visible galaxies would later clump. This ancient blueprint, imprinted in light, directly connects to the vast galaxy surveys we conduct today. The large-scale structure we see, with its immense voids and glittering filaments, matches the patterns predicted by that infant universe. It is a story written in the sky, a narrative that stretches from the first whisper of creation to the grand cosmic architecture we are only now beginning to trace. But if dark matter forms the skeleton, what is the force that seems to be stretching it apart? The silent blueprint of the ancient universe finds its echo in the glittering cities of the modern cosmos. Across the sky, astronomers have embarked on the most ambitious census ever conceived, not of people but of galaxies. This is the third great method for mapping the invisible, a project of cosmic cartography on an unimaginable scale. Imagine a telescope that does not just take pretty pictures, but meticulously records the position and nature of millions of galaxies, building a three-dimensional model of the observable universe. This is the power of a galaxy redshift survey. The most famous of these, the Sloan Digital Sky Survey, has spent decades doing exactly this. Its fundamental tool is a phenomenon called redshift. As the universe expands, it stretches the very fabric of space. Light waves traveling through this expanding space are themselves stretched, becoming longer and redder. The farther a galaxy is from us, the faster it appears to be receding due to the universe's expansion, and the more its light is redshifted. By measuring this redshift with an instrument called a spectrograph, astronomers can determine a galaxy's distance with remarkable precision. It is like hearing a siren from a passing ambulance. As the vehicle moves away, the sound waves stretch and the pitch drops. Redshift is the cosmic version of that dropping pitch, telling us exactly how far away each galactic siren is located. When you plot the positions of millions of these galaxies in 3 dimensions, the hidden skeleton of the universe is suddenly revealed in negative space. The galaxies are not scattered randomly. They cluster into immense walls and filaments, a vast cosmic web that stretches for hundreds of millions of light years. Between these brilliant threads lie unimaginably large voids, regions of near total emptiness that can span hundreds of millions of light years across. This is the architecture of the cosmos, and the galaxies are merely the illuminated nodes where the underlying dark matter skeleton is densest. The dark matter forms the gravitational wells, and the visible galaxies simply fall into them, tracing out a structure we would otherwise be blind to. Collaborations like the Dark Energy Survey take this even further, using both gravitational lensing and redshift data to weigh the dark matter filaments directly. They are not just mapping the light, they are calculating the mass of the invisible wires holding them in place. So what force is powerful enough to orchestrate this grand design, to coax countless galaxies into aligning along these invisible threads? The answer brings us back to the ghost in the machine, the dark matter itself. Its gravitational pull is the master architect, the sculptor that carved these patterns from the formless early universe. But this grand map reveals another, even more perplexing mystery. The universe is not just expanding, this expansion is accelerating. What unseen force could possibly be stronger than gravity itself, pushing the very fabric of the cosmos apart? The grand cosmic map reveals an architect, but the architect itself remains a ghost. We know dark matter's gravitational handiwork, its immense pull sculpting galaxies and guiding light. Yet its true nature is the central mystery of the dark frontier. What could this substance be? A thing that permeates every corner of the cosmos, yet slips through our most powerful detectors without a trace. Scientists have proposed several compelling candidates, each a fascinating piece of theoretical physics. The leading contender for decades has been a hypothetical entity known as a WIMP, an acronym for Weakly Interacting Massive Particle. As the name implies, these particles would be heavy and, crucially, interact with normal matter only through the weak nuclear force and gravity. This would explain why they are so profoundly dark, completely invisible to our electromagnetic eyes. Another promising candidate is the Action, a particle originally conceived to solve a different puzzle in particle physics. Actions would be incredibly light, potentially trillions of times lighter than an electron, and could flow through the universe like a ghostly, intangible wave. The hunt for these phantoms is underway in extraordinary laboratories. Deep underground, in abandoned mines and beneath mountains, scientists have built ultra-sensitive detectors. These vats of ultra-pure liquid are shielded from cosmic rays by a mile of rock, waiting for the once-in-a-lifetime event where a dark matter particle might bump into an atomic nucleus and create a tiny, measurable signal. Meanwhile, the Large Hadron Collider is trying to create dark matter. By smashing protons together at nearly the speed of light, it recreates the violent conditions of the early universe, hoping that new particles, including WIMP, will flash into existence for a fleeting moment. Yet, despite these monumental efforts, no direct, definitive detection has been made. This persistent silence has led some physicists to propose a radically different solution. What if there is no dark matter at all? What if, on the vast scales of galaxies and clusters, our understanding of gravity itself is simply incomplete? This idea, known as modified Newtonian dynamics or MOND, suggests that gravity behaves differently when it becomes exceptionally weak, the way it is in the outskirts of galaxies. It is a controversial theory, a challenge to Einstein's general relativity, but it has its proponents who point to its ability to explain certain galactic rotations without any invisible matter. The debate is fierce, a testament to just how profound this puzzle is. Whether it is an unknown particle or a rewriting of gravity's rules, the answer promises to reshape our understanding of reality. Ponder this for a moment: the chair you sit on, the air you breathe, all the tangible stuff of our world, accounts for a mere 5% of the cosmos. The rest is this dark, unknown frontier, and as if an invisible skeleton was not enough, we must now confront the force that seems to be tearing its work asunder, a mysterious pressure we call dark energy. The grand cosmic map reveals a universe in a state of rebellion, expanding at a rate that defies its own gravity. In the late 1990s, two independent teams of astronomers made a discovery so shocking it overturned our most fundamental assumptions. They were studying a special kind of stellar explosion, a Type 1, a supernova, which acts as a standard candle. These explosions have a known intrinsic brightness, so by measuring how dim they appear from Earth, we can calculate their precise distance. At the same time, we can measure how much the universe has stretched their light, their redshift. The teams expected to find that the expansion of the universe was slowing down, pulled back by the collective gravity of all matter. Instead, they found the opposite. The most distant supernova were significantly fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing, it was speeding up. Some mysterious repulsive force was overpowering gravity, pushing galaxies apart at an ever-increasing rate. This revelation earned the leaders of the teams the Nobel Prize in Physics in 2011, and the mysterious force was given a name: dark energy. Today, we understand that dark energy is not just a force, it is the dominant component of the cosmos, constituting about 68% of the entire universe. It is the invisible engine driving cosmic destiny, but what could it possibly be? The leading candidate is something Einstein himself conceived of, and then later discarded as his greatest blunder: the cosmological constant. This is not a particle or a field in the traditional sense, but an inherent property of the vacuum of space itself. Think of empty space not as true nothingness, but as a seething foam of virtual particles popping in and out of existence. This vacuum energy exerts a negative pressure, a kind of anti-gravity that causes space to expand. As the universe grows, more space is created, which in turn creates more repulsive dark energy, leading to a self-perpetuating cycle of acceleration. Another theory proposes a dynamic field called Quintessence, a fluid that permeates all of space and whose strength can change over time. The debate between these models is one of the most active in all of cosmology. How does this accelerating force interact with the dark matter skeleton? It is a cosmic tug of war on the grandest possible scale. While dark matter's gravity works tirelessly to pull the cosmic web together, weaving galaxies into filaments, dark energy works to stretch and tear that fabric apart. It is as if the invisible steel beams holding up a city were simultaneously being pulled outward by an immense, unseen pressure. Supercomputer simulations are our only window into this epic struggle. They model how these two dark components, one clumping and one pushing, have shaped the universe's evolution. By running the clock forward, these simulations reveal a chilling potential future, one where the acceleration becomes so dominant that the cosmic web is ultimately shredded, leaving galaxies isolated and alone in an ever-expanding, ever-cooling void. This epic struggle between dark energy and dark matter unfolds not in real time, but inside the memory of the world's most powerful supercomputers. To understand a cosmos we cannot directly see, we must build our own. Scientists create virtual universes from scratch, starting with the smooth, hot soup of the Big Bang and programming in the known laws of physics, especially the relentless pull of gravity from dark matter. The most famous of these digital cosmos projects is the Millennium simulation. It began with over 10 billion virtual particles representing dark matter, each one a seed of potential structure, and set them adrift in a simulated expanding space. The computers then calculated the gravitational dance between every single one of those particles over billions of years of cosmic evolution. The results are breathtaking. From that formless digital void, a familiar architecture spontaneously emerges. A vast, intricate cosmic web materializes on the screen, with dark matter filaments snaking between massive halos and immense empty voids opening up between them. It is a ghostly, digital twin of the universe we observe through our telescopes. The initial conditions for these simulations are not random guesses. They are fed directly from the cosmic microwave background, that ancient blueprint of the infant universe. The subtle variations in that first light become the starting points for the dark matter to begin its clumping. The simulation then runs the cosmic clock forward, showing us how gravity amplifies those tiny seeds into the grand structures we see today. The output is more than just a pretty animation. It predicts where and when galaxies should form within the dark matter halos, creating a timeline of cosmic evolution that astronomers can compare directly to real data from galaxy surveys. The match is often astonishingly precise, a powerful confirmation that our models of the dark skeleton are fundamentally correct, yet a profound question remains. Can a simulation, no matter how complex, ever truly capture the full, messy reality of the cosmos? It is a model, a simplification built on our current and likely incomplete understanding of physics. These virtual universes are our best guides into the dark frontier, but they are also a reminder that we are still piecing together the rules of the game. The ultimate test is to compare these digital prophecies with an actual, three-dimensional map of the real cosmos, a project now underway on a scale once thought impossible. The silent predictions of supercomputers are now meeting the hard light of reality as a new generation of cosmic cartographers rises to the challenge. Scattered across mountaintops and soon to be launched into the void, an alliance of powerful instruments is turning our virtual models into an actual atlas of the invisible. This is not the work of a single telescope, but a global symphony of observation, a coordinated effort to map the dark frontier with a precision once thought impossible. At the Kitt Peak National Observatory in Arizona, the Dark Energy Spectroscopic Instrument, known as DESI, is conducting one of the most ambitious surveys ever conceived. Its goal is to capture the spectra of over 30 million galaxies and quasars, measuring their redshifts to pinpoint their locations in three-dimensional space. Imagine a robotic array of 5,000 tiny, automated fibers, each one precisely positioned to siphon the light from a single, distant galaxy. Night after night, this incredible machine is building a cosmic city plan on a scale that spans billions of light years. Meanwhile, the European Space Agency's Euclid Space Telescope is poised to join this grand endeavor from its vantage point beyond Earth's atmosphere. Euclid is designed as a surveyor of the unseen, equipped with a wide-field camera that will image billions of galaxies to measure the subtle distortions of weak gravitational lensing. It will trace the dark matter filaments directly, weighing them by the way they bend the light of countless background stars. These projects are monumental international collaborations, involving thousands of scientists from dozens of countries, all pooling their data and intellect to see the bigger picture. As one project scientist for DACY noted, the sheer volume of data is transformative. We are no longer studying individual galaxies, but the entire cosmic ecosystem. The technological leaps enabling this are staggering. The cameras have become so sensitive they can detect the faint glow of a galaxy over 10 billion light-years away. The data processing algorithms must sift through petabytes of information, identifying and measuring billions of celestial objects automatically. This is astronomy at an industrial scale, a far cry from an astronomer peering through a single eyepiece. We are collectively building the most comprehensive three-dimensional map of the universe ever attempted, a chart that will show the dark matter skeleton in more detail than ever before. Yet, for all this technological might, the path to mapping the invisible is fraught with immense and surprising obstacles. Mapping the invisible cosmos is like trying to find a needle in a haystack while wearing a blindfold. The haystack is the entire universe, and the needle is a substance that refuses to touch light. Our technological reach is staggering, but it is perpetually brushing against its own limits. The detectors buried deep underground must be shielded not just from cosmic rays, but from the faint, natural radioactivity of the very rock that surrounds them. A single radioactive decay in the detector's own components can mimic the elusive signal of a dark matter particle collision, creating a maddening background chatter that obscures the truth. From above, the constant rain of cosmic particles and the subtle glow of atmospheric airglow create a veil of interference, a cosmic noise that astronomers must meticulously filter out of their data. The faint, coherent warping of weak gravitational lensing is so subtle that it can be drowned out by the natural, random variations in the shapes of galaxies themselves. It is only by averaging the shapes of millions of galaxies that the ghostly signature of the dark matter skeleton emerges from the statistical noise. The theoretical challenges are just as profound. We are hunting for something whose fundamental properties we do not know. Is dark matter cold, meaning its particles move slowly, or is it warm, with particles moving at a significant fraction of light speed? Is it made of one type of particle, or a whole hidden sector of dark particles interacting through their own dark forces? Each possibility leads to a different predicted structure for the cosmic web, forcing us to refine our supercomputer simulations and our observations in a constant, iterative dance. This uncertainty is mirrored in the mystery of dark energy. The simplest model, the cosmological constant, comes with its own profound puzzle, known as the fine-tuning problem. The predicted strength of this vacuum energy, based on our best theories of quantum physics, is astronomically, unimaginably larger than what we actually observe. The discrepancy is a factor of 1 followed by 120 zeros. It is the worst prediction in the entire history of physics, a screaming void in our understanding that suggests we are missing something fundamental about the nature of reality. These tensions are not just philosophical, they show up in the data itself. A major controversy known as the Hubble tension has divided cosmologists. Different methods for measuring the universe's current expansion rate, one using the cosmic microwave background and another using supernova and other local markers, are yielding stubbornly different answers. They disagree by just enough to be statistically significant, suggesting a crack in our standard model of cosmology. Could this mean dark energy is not a constant, but has been evolving over billions of years? Or does it point to entirely new physics waiting to be discovered? So how do scientists navigate this labyrinth of unknowns? They turn inconsistency into a guide. Every failed experiment narrows the territory where dark matter can hide. Every theoretical tension, like the Hubble tension, becomes a focal point for new ideas and more precise measurements. The struggle itself is the engine of discovery, forcing innovation in detector technology, data analysis, and fundamental theory. The very act of confronting these immense hurdles is what paves the way for the next great leap into the dark. These immense datasets are a new kind of cosmos, a digital universe of numbers and pixels that no single human could ever fully explore. Within this sea of information, a new partner has emerged in the search: artificial intelligence. Specially designed machine learning algorithms are now sifting through petabytes of astronomical data, finding patterns and connections that are completely invisible to the human eye. These are not sentient machines, but sophisticated tools trained to recognize the faint fingerprints of cosmic phenomena. One of their most vital roles is in classifying galaxies. A single sky survey can image billions of galaxies, each one a unique swirl or ellipse. Having astronomers manually sort them by shape and type would take centuries. Instead, AI models are trained on vast catalogs of pre-classified galaxies, learning the subtle visual cues that distinguish a spiral from an elliptical or a distant, merging galaxy from a nearby one. This automated taxonomy is the first, essential step in building an accurate cosmic map, but AI goes far beyond simple sorting. It is a master at detecting the subtle signatures of gravitational lensing. The weak distortions that reveal dark matter are so slight that they are lost in the natural irregularities of galaxy shapes. Machine learning algorithms, however, can be trained to see through this randomness. They learn the statistical hallmarks of coherent shearing, identifying the collective warping caused by an invisible mass, even when no single galaxy appears clearly bent. This allows us to trace the faintest tendrils of the cosmic web with unprecedented clarity. Perhaps most powerfully, AI is now helping to design the surveys themselves. The upcoming Legacy Survey of Space and Time, or LSST, at the Vera C, Rubin Observatory will generate a mind-boggling amount of data every single night. It is impossible to point the telescope at everything, so AI-driven software is used to optimize the survey strategy in real time. It can prioritize which patches of sky to observe for the most scientifically valuable results, perhaps focusing on a region where a supernova is predicted to explode or where lensing events are most likely. As one data scientist working on the project remarked, "We are no longer just using telescopes. We are collaborating with an intelligent system that guides our gaze." This is a fundamental shift in how we do science. The AI does not replace the scientist, it augments our perception, allowing us to see a deeper, richer universe. Yet this powerful partnership raises profound questions. Can we fully trust a black box algorithm whose decision-making process we do not entirely understand? If an AI identifies a new type of cosmic structure, how do we verify its discovery? The ethics of relying on intelligent machines for fundamental discovery is a new frontier in itself. This challenge forces cosmologists, computer scientists, and philosophers to work together, making the search for the invisible skeleton one of the most interdisciplinary endeavors in human history. The search for the universe's hidden skeleton demands more than a single perspective. It requires a grand collaboration, a fusion of minds from fields that once seemed worlds apart. Particle physicists who study the impossibly small now work hand in hand with cosmologists who study the impossibly large. Their shared target is dark matter. Deep underground, in experiments like LUX Zeppelin and Xeno NNT, particle physicists have built ultra-sensitive traps. These are not telescopes, but exquisitely tuned instruments designed to catch the faintest whisper of a collision, a single dark matter particle interacting with a xenon atom. They operate in a silence deeper than any found in nature, shielded from the constant noise of the cosmos, waiting for a signal that has not yet come. This silence itself is a form of data, systematically ruling out entire classes of potential particles and forcing theorists back to their chalkboards. The dialogue between the underground labs and the theorists is constant. A null result from a detector can be as influential as a discovery. narrowing the hunting ground and refining our ideas about what the dark skeleton is truly made of. Meanwhile, computer scientists provide the stage where this cosmic drama can play out. They are the architects of virtual universes, writing complex code that translates the abstract mathematics of gravity and particle physics into breathtaking digital cosmologies. Their supercomputers are the only laboratories where we can watch galaxies form and dark matter filaments weave themselves together over billions of years. This synergy creates a powerful cycle. Observational astronomers map the real sky. Theorists develop models to explain the map. Computer scientists simulate those models. And then astronomers compare their real data to the simulation, checking for a match. Any discrepancy is not a failure, but a clue, pointing toward new physics or a flaw in our understanding. This cross-pollination of ideas sometimes leads to radical possibilities. String theory, a framework that attempts to unify all forces of nature by proposing tiny, vibrating strings as the fundamental constituent of matter, was once purely a mathematician's playground. Today, its ideas actively inform cosmology. Some string theory models predict a whole hidden sector of particles, a dark world with its own forces and interactions, which could explain why dark matter behaves the way it does. While still speculative, this fusion of the most theoretical physics with the most concrete observations shows how boundaries are blurring in the face of a shared mystery. Solving a puzzle of this scale is not a solitary pursuit. It is a testament to collective human curiosity, where the insight of a programmer optimizing an algorithm is as crucial as the intuition of a physicist devising a new theory. This collaborative spirit forces us to ask a deeper question, one that moves beyond the machinery of discovery. If our entire reality is built upon a foundation we cannot see, what does that say about the very nature of what is real? Our own senses are a cage, a prison of perception built for survival on a single planet. They were never designed to comprehend the cosmos. We live in a world defined by light and touch, yet the universe is overwhelmingly composed of realities we cannot see or feel. This is the deepest philosophical shock of the dark frontier. It forces us to confront a humbling truth. The reality we experience is a mere sliver, a specialized interface, while the true nature of existence operates on a level fundamentally beyond our biological grasp. The German philosopher Immanuel Kant wrestled with this very problem centuries ago. He distinguished between the phenomenal world, the world as it appears to our senses, and the noumenal world, the world as it truly is in itself. He argued that we can never directly know the noumenal realm. We are forever trapped interpreting it through the filters of our minds, through concepts like space and time. Dark matter and dark energy are the ultimate validation of Kant's idea. The glittering galaxies we see are the phenomenal universe, the pretty surface. But the dark skeleton and the repulsive energy are the noumenal reality, the true cosmos that we infer through mathematics and its gravitational effects, but can never directly touch or see. This raises a deeply unsettling question. Can our science, a tool built by minds evolved to avoid predators and find food, ever truly unravel a universe where 95% of the content is invisible? We are like fish trying to develop a theory of water. We are so immersed in our own normal matter reality that we struggle to conceive of the rules governing the rest. Every discovery we make seems to push the ultimate truth further away. The more we learn about dark matter, the more we realize how little we know about what it actually is. The more we measure dark energy, the more perplexing its behavior becomes. This is not a failure of science. It is a revelation about its limits. We are mapping the shoreline of an ocean of ignorance, and with every new inch of coast we chart, the vast, dark sea beyond seems to grow larger. Our entire history of cosmology is a story of these Copernican shocks, each one removing us further from the center of things. We once thought Earth was the universe. Then we learned it was just a planet orbiting the sun. Then we discovered the sun was one average star among billions in a galaxy. Then that our galaxy was one of countless others. Now we are learning that all those galaxies are just the visible froth on a dark cosmic ocean. Each step has been a lesson in cosmic humility. So where does this leave our quest for understanding? It transforms it from a simple hunt for answers into a profound metaphysical journey. We are not just cataloging stars. We are asking what it means to exist in a universe where the dominant forces are, and may forever remain, hidden from our direct experience. This journey forces us to look back, to see how our ancestors grappled with the unseen, and how our own models of reality have been torn down and rebuilt time and again. Our ancestors gazed at the star-dusted night sky and saw the work of gods and giants. For millennia, human explanations for the cosmos were woven from myth and metaphysics. The Norse believed a great world tree, Yggdrasil, held the 9 realms in its branches. The ancient Greeks told of Atlas, a titan condemned to hold up the celestial spheres for eternity. These were powerful, imaginative answers to a fundamental question. What holds it all up? The scientific revolution began a profound shift, replacing divine beings with mathematical laws. Isaac Newton, upon observing an apple fall, realized the same force pulling the fruit to the ground also kept the moon in its orbit around Earth. He gave us a universal law of gravitation, a single mathematical rule that could predict the motions of planets and comets. The universe was no longer a realm of capricious deities, but a grand, predictable clockwork. Yet Newton's clockwork had its limits. His laws described the force of gravity beautifully, but he was deeply troubled by a simple question. How does gravity actually work? How does the sun reach across 93 million miles of empty space to pull on the Earth? He called this mysterious, instantaneous action at a distance an absurdity, but he had no mechanism to explain it. The answer would not come for another 2 centuries from a patent clerk in Switzerland. Albert Einstein's theory of general relativity completely reimagined the cosmos. He proposed that gravity is not a force pulling through space, but a curvature of spacetime itself. A massive object like the sun creates a dip in the fabric of the cosmos, and the Earth simply follows the curve of that dip, like a marble rolling around a funnel. This was the breakthrough that made modern cosmology possible, providing the language to describe an expanding universe and the bending of light. These conceptual leaps were always driven by new tools. Galileo's simple telescope revealed moons orbiting Jupiter, challenging the Earth-centered universe. Edwin Hubble's powerful instrument at Mount Wilson Observatory then revealed that those faint, spiral nebulae were not clouds within our own galaxy, but entire galaxies themselves, rushing away from us in an expanding cosmos. Each new window into the sky shattered an old assumption and built a new one. This progress was never smooth. It was forged in the fires of fierce debate. In the early 20th century, a great controversy erupted over the age of the universe. Hubble's initial measurements of the expansion rate suggested the cosmos was younger than the Earth itself, a clear impossibility. This conflict between astronomy and geology was only resolved decades later with more precise data, revealing a much older and vaster universe. This pattern repeats through history. A crisis in data, a clash of ideas, and eventually a new paradigm emerges. So how does this long arc of discovery inform our current quest? It teaches us that every answer is temporary, a stepping stone to a deeper mystery. Newton's gravity led to Einstein's spacetime, which in turn led us directly to the dark frontier. We are living through the next great controversy, the next clash of data and theory, just as Hubble and his contemporaries did. Our tools are now digital, our maps 3-dimensional, but the essential human drive remains the same, to look into the darkness and demand to know what is there. This legacy of curiosity is not just for scientists in ivory towers. It belongs to everyone who has ever looked up at the night sky and wondered. And that is precisely why the story of the dark frontier must be shared far beyond the pages of academic journals, becoming a vital part of how we educate the next generation. The legacy of cosmic curiosity is no longer confined to textbooks. It is spilling out into classrooms and glowing on the screens of planetarium domes, where interactive exhibits transform abstract theories into tangible experiences. Imagine a child using a touchscreen to warp a virtual spacetime fabric, watching how a dark matter halo bends the path of starlight. These are not just games, they are gateways. The most powerful tool for this outreach is citizen science, a movement that invites everyone to become a co-discoverer. Platforms like Zooniverse connect the public directly with the frontiers of research. Anyone with an internet connection can help astronomers by looking at real telescope images, classifying galaxy shapes, or even spotting the subtle arcs of gravitational lenses that computer algorithms might have missed. This is not busy work. These collective human decisions have led to genuine discoveries, published in scientific papers with the volunteers listed as co-authors. One educator involved in these programs explained, when a student realizes their own curiosity can contribute to a global project, it transforms science from a subject to be memorized into a living, breathing adventure they are a part of. Making these complex topics accessible is not about dumbing them down. It is about building a bridge from wonder to understanding, showing that the grand questions of the cosmos are not just for experts in lab coats, but for anyone willing to look up and ask why. How might you contribute to this grand endeavor? The journey to map the invisible cosmos is a monumental human project, one that requires not just brilliant minds, but vast resources and a global commitment. This grand endeavor of cosmic mapping carries a staggering price tag. The tools for this exploration are not simple backyard telescopes, but billion-dollar instruments requiring vast international consortia and decades of sustained funding. The James Webb Space Telescope, a technological marvel now peering deeper into the cosmos than ever before, is a prime example of the financial realities. Its initial budget was set at $500 million, but through technical challenges and delays, its final cost soared to nearly $10 billion. This ignited public debate about the value of such expensive science when so many earthly problems demand resources. Yet these projects are not frivolous expenses. They represent a deliberate investment in fundamental knowledge, a long-term bet on the human spirit of inquiry. The funding for this work comes from a delicate partnership between government agencies like NASA and the European Space Agency, and increasingly from private foundations and visionary philanthropists. These entities must constantly weigh the abstract goal of understanding the universe against the immediate need for tangible returns. The justification often lies in the cascade of unexpected spin-off technologies that these ambitious projects generate. The need to capture faint light from the edge of the universe drove the development of more sensitive infrared sensors, which are now used in medical imaging to detect cancers earlier. The algorithms created to analyze gravitational lensing have been adapted to improve facial recognition software and autonomous vehicle navigation. Even the precision mirrors of the Webb telescope have advanced techniques used in laser eye surgery. These are not the goals of the research, but they are its powerful and practical byproducts. Securing long-term funding for a project that might not produce answers for a generation is a constant battle. Politicians and the public rightly ask what they will get for their money when the primary return is simply knowing. This forces scientists to become advocates, translating the profound mystery of dark matter into a compelling narrative that resonates with the human desire for exploration. The true value may be immeasurable, lying not in a new gadget, but in the fundamental reshaping of our self-understanding within the cosmos. This raises a deeper question about the nature of progress itself. If we only fund what we know will have an immediate use, do we risk extinguishing the very curiosity that leads to the most transformative discoveries of all? That staggering $10 billion price tag for a space telescope is not just an expense. It is an investment that ripples back to Earth in unexpected and profoundly human ways. The relentless drive to see the invisible cosmos has, time and again, gifted us new ways to see ourselves. The digital camera in your smartphone owes its existence to the stars. In the 1970s, astronomers grew frustrated with photographic plates. They were inefficient, capturing only a tiny fraction of the light from distant galaxies. The solution was the charge-coupled device, or CCD, a sensor that could convert light directly into digital signals with incredible sensitivity. Developed for telescopes to peer into the deepest voids of space, CCD technology was quickly adapted for everyday use, revolutionizing photography, medicine, and communication. Today, the same fundamental technology that images the cosmic web also powers the camera that lets you video call a loved one across the globe. This pattern of cosmic spin-offs is everywhere. The need to analyze the faint, distorted light from gravitational lensing pushed the development of sophisticated image processing algorithms. These very same algorithms are now used in medical MRI machines, helping doctors to detect subtle tumors in the human brain with far greater clarity. The intricate software designed to map the dark matter skeleton is now being applied to model the complex neural networks of our own minds. Even the precise atomic clocks on GPS satellites must be constantly corrected for Einstein's theory of relativity. Without accounting for the subtle warping of space-time by Earth's gravity, your navigation app would guide you astray by several miles within a single day. Our quest to understand the universe's expansion directly keeps you from getting lost on your way to the grocery store. This raises a vital question for society. How do we value knowledge for its own sake? Pure research into dark matter has no obvious, immediate market application. Its goal is fundamental understanding. Yet, by pushing against the absolute limits of technology, it consistently forces breakthroughs that eventually reshape our daily lives. The World Wide Web itself was invented at CERN, the particle physics laboratory, to help scientists share data about the fundamental nature of matter. The innovation did not come from a goal to create a global communication network, but from the sheer necessity of solving a cosmic-scale puzzle. The materials developed to shield ultra-sensitive dark matter detectors from background radiation are now informing new designs for safer nuclear reactors. The supercomputers built to simulate the universe are now being used to model climate change and develop new pharmaceuticals. When we fund the search for an invisible cosmic skeleton, we are also investing in a boundless engine of earthly innovation. But the impact of this journey extends far beyond the devices we hold in our hands. It seeps into our art, our stories, and our very sense of what it means to be a small, curious species in a vast and mysterious cosmos. This hidden architecture of the cosmos has escaped the confines of the laboratory, spilling over into our collective imagination. Filmmakers and artists are increasingly drawing from the language of cosmology to tell new kinds of stories. The vast, invisible web of dark matter becomes a perfect metaphor for the unseen connections that bind a universe or a society together. In the film Interstellar, the depiction of a tesseract, a higher dimensional space where time becomes a physical dimension, is a direct attempt to visualize concepts from theoretical physics. The alien megastructures in science fiction, like the Dyson sphere, echo our own attempts to find order and intelligence within the cosmic dark. These are not just special effects, they are philosophical arguments rendered in light and sound. Abstract painters, too, are captivated. They create swirling, dark canvases punctuated by brilliant nodes of light, directly inspired by maps of the cosmic web. These artworks do not explain the science, but they capture its emotional core, the awe and humility of confronting a reality mostly hidden from view. One digital artist who uses supercomputer data to generate their visuals explained that their work is a translation. They are trying to build a bridge between the cold data of a simulation and the human feeling of wonder. This cultural feedback loop is vital. Science provides the raw, thrilling material, and art processes it into stories and images that the public can feel. This, in turn, generates more widespread fascination, which fuels support for the scientific missions themselves. Our myths have always been shaped by our best understanding of the world. We have moved from gods holding up the sky to gravitational wells and quantum foam. This ongoing dialogue between the scientist and the artist ensures that the greatest story ever told, the story of the universe, continues to be told in 1,000 different ways. And you do not need a billion-dollar telescope to participate in this next great chapter of discovery. Your own curiosity can become a vital instrument in this grand search. Across the internet, a quiet revolution is unfolding, where everyday people are partnering with professional astronomers to map the dark frontier. Platforms like Zooniverse host citizen science projects that invite anyone with a web browser to sift through real telescope data. You might be presented with a gallery of distant galaxies and asked a simple question: is this a smooth ellipse, a majestic spiral, or a chaotic merger? This is not a game. Each classification is a crucial data point, helping machines learn and assisting researchers in categorizing billions of celestial objects far faster than any single team could manage. The human brain possesses an unmatched ability for pattern recognition, spotting subtle oddities that even the most sophisticated algorithms might overlook. This collective effort has led to stunning discoveries. A retired schoolteacher in Scotland, clicking through images on the Galaxy Zoo project, noticed a strange, greenish smudge that did not resemble any known galaxy. Professional astronomers investigated and confirmed it was a completely new type of object, a gas cloud illuminated by a quasar, now known as Hani's voorwerp, which is Dutch for Hani's object. Another volunteer, sifting through data from the Kepler Space Telescope, identified the bizarre and now famous star known as Tabby's star, whose wild, unpredictable dimming patterns continue to baffle scientists. These are not isolated incidents. In one project focused on gravitational lensing, volunteers discovered dozens of new lens candidates, rare cosmic mirages that are crucial for weighing dark matter, simply by looking for the faint, telltale arcs that computer programs had missed. This massive, distributed workforce accelerates research by years, turning the impossible task of analyzing a sky full of data into a manageable, collaborative human endeavor. It democratizes discovery, proving that you do not need a PhD to contribute to the cutting edge of cosmology. What does it mean when a grandmother in Ohio and a taxi driver in Mumbai can both help trace the invisible skeleton of the universe? It transforms science from an elite pursuit into a shared human journey, a testament to the power of countless small observations adding up to a profound new vision. This collective effort reveals a universe not just of hidden forces, but of boundless human potential. A cosmic collision 1.7 billion light-years away delivered the most direct proof of the invisible skeleton. Two immense galaxy clusters, each containing thousands of galaxies, slammed into one another at a phenomenal speed. This event, known as the Bullet Cluster, created a perfect natural experiment. Scientists observed the aftermath using two different eyes. The Chandra X-ray Observatory saw the hot gas, the normal matter of the clusters. This superheated plasma, the most abundant visible substance, slammed together during the collision and got stuck in the middle, like two clouds of smoke merging. But when astronomers mapped the mass using gravitational lensing, by measuring how the collision zone warped the light of background galaxies, they found the true bulk of the clusters was not in the center. The majority of the mass, the dark matter, had sailed right through the cosmic wreck and kept going. It left the visible gas behind. This happened because dark matter, unlike normal matter, does not interact with itself or anything else through the electromagnetic force. There was no friction to slow it down. The particles passed through each other like silent ghosts, while the normal gas particles collided and piled up. The result was a clean separation of the universe's components. The dark matter formed two distinct clumps on either side of the collision, far from the glowing ball of trapped gas in the center. One astronomer described the finding as seeing a ghost walk through a wall, leaving its visible body behind. The bullet cluster became a landmark in cosmology. It was not just more circumstantial evidence, it was a direct observation of dark matter behaving exactly as a particle should, and not as a modification of gravity would predict. The discovery sent ripples of excitement through the scientific community, hailed as a smoking gun that cemented the reality of the dark cosmic web. If one collision can reveal so much, what other secrets are hidden in the wreckage of other cosmic crashes? These ghostly collisions are just the beginning. The next leap in our vision is already taking shape on remote mountaintops and in clean rooms awaiting launch. A new era of cosmic cartography is dawning, led by observatories so powerful they will map the sky not in years but in nights. In the Chilean Andes, the Vera C. Rubin Observatory is preparing for a mission of pure speed and scale. Its core instrument is the largest digital camera ever built for astronomy, a 3.2 billion pixel eye that will capture an area of sky equivalent to 40 full moons in a single exposure. Night after night for a decade, it will perform a grand inventory of the southern sky, not once but over and over. This relentless scanning, known as the legacy survey of space and time, will create a cosmic movie. It will catch billions of subtle changes, from exploding stars to asteroids moving across our solar system, all while measuring the shapes of billions of galaxies to trace the dark matter web with more precision than ever before. Its sweeping gaze is perfectly complemented by the sharp, deep vision of the Nancy Grace Roman Space Telescope. Scheduled to launch later this decade, Roman is often called Hubble's wide-eyed cousin. It will combine Hubble's incredible image clarity with a field of view 100 times larger. This allows it to conduct vast surveys at high resolution, peering back across billions of years to see how the cosmic web has evolved. Roman's primary mission is to tackle the mystery of dark energy. It will use 3 independent methods, measuring the distances to millions of exploding stars, mapping the 3-dimensional positions of countless galaxies, and observing how giant clusters of galaxies have formed over cosmic time. By cross-referencing these different probes, scientists hope to finally determine if dark energy has remained constant, as the cosmological constant suggests, or if its strength has changed, pointing toward a more dynamic field like Quintessence. This multi-pronged attack is designed to resolve the simmering cosmological tensions. The Hubble tension, the stubborn discrepancy in the universe's expansion rate, could finally crack open under the weight of this new, pristine data. These observatories are not just bigger telescopes, they are smarter systems. They are equipped with artificial intelligence that will make real-time decisions, instantly flagging unusual events for follow-up and optimizing the survey minute by minute. What could they find? The most exciting possibilities are the ones we cannot yet predict. They might reveal that dark energy is not a constant force, but a decaying field, which would completely alter our forecast for the universe's ultimate fate. They could discover that the dark matter particle is not a single entity, but a whole family of particles, a hidden sector with its own rich physics. Every strange, unexplained flicker in their data could be a thread leading to a new chapter in physics. These missions are built on the conviction that to find answers, we must first gather light on a scale that was once pure fantasy. They are our best chance to move from inferring the dark skeleton to understanding its fundamental nature, but mapping its gravitational influence is only one path. What if we could finally catch a single piece of this ghostly substance, deep beneath the surface of our world, in the profound silence of abandoned mines and mountain caverns? The most patient hunt in history is underway. These laboratories are buried under a mile of solid rock, shielded from the constant barrage of cosmic rays that would otherwise drown out the faintest of whispers. Here, scientists have built the most sensitive ears on the planet, designed to listen for a ghost. The heart of these experiments is often a vat of ultra-pure liquid xenon, chilled to -100 degrees Celsius. In the pitch darkness of this cryogenic bath, the hope is that a particle of dark matter, after its journey across the cosmos, will finally bump into the nucleus of a xenon atom. This collision, however faint, would produce a tiny flash of light and a wisp of free electrons, a dual signal that detectors are poised to capture. This is the promise of experiments like LUX Zeppelin in South Dakota and Xeno NNT in Italy, which represent the cutting edge of direct detection. Their names are acronyms for their complex technologies, but their goal is beautifully simple: to catch a single piece of the invisible skeleton. Yet the challenge is monumental. The expected signal is incredibly rare, with perhaps just a handful of genuine interactions expected per year in a ton of xenon. The real enemy is background noise. The very walls of the detector, the surrounding rock, even the air, all emit trace amounts of natural radioactivity. A single radioactive decay from an atom in the detector itself can mimic the signature of a dark matter collision. To combat this, every component is meticulously selected for its ultra-low radioactivity, and the liquid xenon is constantly purified. Scientists spend years characterizing and subtracting this background chatter, searching for the irreducible signal that could only come from the dark frontier. Researchers who dedicate their lives to this work often speak of a quiet, persistent excitement. One physicist described it as maintaining a state of constant vigilance, knowing that the next tick of the data could be the one that rewrites the textbooks. There is a profound sense of responsibility, of being a gatekeeper for a discovery that would fundamentally alter our place in the cosmos. This hunt demands immense patience. It is a pursuit measured not in weeks or months, but in decades, across generations of ever more sensitive detectors. The continued silence, the absence of a definitive signal, is itself a powerful result. It systematically closes doors, telling us what dark matter is not, and forcing us to refine our theories and consider more exotic possibilities. This very patience, this willingness to sit in the dark and listen, is a testament to the human drive to know, even when the answers remain stubbornly out of reach. Perhaps the ghost is not a particle at all, but a flaw in our understanding of gravity itself. This is the radical proposition of modified Newtonian dynamics, or MOND. It suggests that on the vast, sparse scales of galactic outskirts, where gravitational pull becomes almost immeasurably weak, Isaac Newton's and even Albert Einstein's laws need a tweak. Instead of invoking an invisible substance, MOND proposes a simple adjustment to the equations of motion. It is the cosmic equivalent of discovering your car's speedometer has been slightly miscalibrated all along. For certain galaxies, especially those with a uniform rotation, MOND works remarkably well. It can predict the high orbital speeds of stars without requiring any dark matter halo, offering an elegant solution that dispenses with the need for a mysterious, unseen component. This has made it a compelling alternative for a small but dedicated group of physicists. Yet for the majority of cosmologists, the evidence for a tangible dark matter particle remains overwhelming. MOND struggles to explain the bullet cluster, where the gravitational mass clearly separated from the visible matter. It has a difficult time accounting for the precise patterns in the cosmic microwave background, which are perfectly explained by dark matter's gravitational influence in the early universe. Think of it like a recipe, the standard model of cosmology with its ingredients of dark matter and dark energy can bake a cake that matches the one we see out our telescopes. MOND can sometimes get the flavor of a single slice right, but it fails to recreate the entire complex dessert. The debate between these two camps is not a weakness in science, but its greatest strength. It embodies the principle of falsifiability, where every theory must make predictions that can be tested and potentially proven wrong. This constant, rigorous challenge is what pushes our understanding forward. How do such monumental paradigm shifts actually happen in science? They do not occur because a single experiment delivers a verdict, but through the gradual accumulation of evidence that the old framework can no longer explain. We are living through that exact process now, a slow-motion revolution in our cosmic perspective. The outcome will not only tell us what holds galaxies together, but will ultimately determine the final fate of everything we see. The fate of the cosmos hinges on the nature of that which we cannot see. Dark energy, the mysterious force accelerating the universe's expansion, is not just a curious phenomenon. It is the author of our ultimate destiny. Scientists have mapped out several possible endings, cosmic stories written by the strength and character of this dark pressure. The most gentle of these conclusions is known as the Big Freeze or heat death. In this scenario, dark energy maintains a constant strength, much like Einstein's cosmological constant. The expansion continues to accelerate, gently but inexorably. Over trillions of years, galaxies will be pulled so far apart that the sky beyond our own local group will go completely black. Stars will burn through their fuel and wink out one by one. Eventually, even black holes will evaporate through a process known as Hawking radiation, leaving behind a universe that is a cold, dark, and nearly empty sea of isolated particles and fading radiation. It is a quiet, slow dissolution into maximum entropy, where the cosmos simply runs out of usable energy. A more violent alternative is the Big Rip. This fate unfolds if the repulsive force of dark energy actually strengthens over time. Instead of a constant pressure, imagine a force that grows more powerful as the universe expands. In this scenario, dark energy's density increases and its grip becomes absolute. First, it would tear apart galaxy clusters, then individual galaxies. As the end nears, the very fabric of space itself would expand faster than the speed of light at a local level. Stars and planets would be ripped apart. Finally, in a final, terrifying instant, atoms themselves would be shredded, and the building blocks of matter would be torn asunder. The universe would end not with a whimper, but with a catastrophic, fundamental unraveling. The deciding factor between these fates is a number known as the equation of state parameter, symbolized as W. This number describes the relationship between the pressure and density of dark energy. If W is exactly -1, we get the Big Freeze. If it is less than -1, say -1.1, we are headed for the Big Rip. Every observation we make with telescopes like Hubble, Daisy, and the future Roman mission is in essence an attempt to measure this single, crucial number with ever greater precision. So where do current observations point? The data overwhelmingly favors a value very close to -1. The cosmological constant, and thus the Big Freeze, remains the most likely outcome based on everything we currently know. Yet the uncertainty in our measurements leaves the door slightly ajar for more dramatic possibilities. As one leading cosmologist reflected, we are in the peculiar position of predicting the end of all things from a handful of faint supernova and warped galaxies. It is a profound responsibility to use the finite light we can gather to forecast an infinite darkness. These are not just abstract calculations. They are prophecies written in the language of physics. What does it mean for us, conscious beings living on a tiny planet in a single galaxy, to contemplate the end of everything? Our sun will die long before these cosmic endings. Our galaxy will merge with others, and all traces of human existence will likely be erased eons before the final curtain falls. This knowledge carries a strange and heavy philosophical weight. It can feel nihilistic, suggesting that nothing ultimately matters. Yet many scientists and philosophers see a different message. The fact that we can peer across billions of light years and billions of years to understand our place in this grand narrative is itself a miracle. Our fleeting moment of consciousness is the universe's way of understanding itself, even as it races toward its own conclusion. This cosmic perspective forces a difficult question. If our time is so brief and our physical legacy so temporary, what is the true value of our actions, our art, and our ethics? How should we behave in a universe that is ultimately transient? Our ability to map the invisible cosmos carries a profound responsibility. With every new discovery about the universe's fundamental workings, we gain not just knowledge but power. The same physics that describes dark matter's gravitational pull could, in theory, one day be harnessed in ways we cannot yet foresee. History shows us that fundamental research, from nuclear fission to genetic engineering, can be a double-edged sword, offering both immense benefit and potential for catastrophic misuse. The ethical question is not whether we should pursue this knowledge, but how we ensure it serves to unite and elevate humanity, rather than divide or destroy it. This cosmic perspective inherently pushes against division. When we see Earth as a fragile, pale blue dot set against the vast dark frontier, national borders vanish. The project to map the cosmic web is a powerful example, a collaboration uniting scientists across continents, cultures, and political divides in a shared, peaceful quest for understanding. This model of global cooperation, forged in the pursuit of pure knowledge, becomes a beacon, suggesting that our greatest challenges, both cosmic and earthly, can only be met together. This viewpoint also reshapes our relationship with our own planet. Understanding the universe's rarity and fragility, the delicate balance that allowed life to emerge on this single world, fosters a deep-seated environmental stewardship. If the cosmos is mostly an inhospitable void of dark matter and empty space, then our vibrant, living Earth is not just our home, but a sacred trust. This leads to a difficult and necessary debate. How do we justify spending billions on space telescopes and particle detectors when poverty, disease, and climate change demand urgent resources here on Earth? The argument is not trivial. It forces a vital conversation about our priorities, yet the choice is rarely so binary. The technological and philosophical returns from cosmic exploration often provide the very tools and perspective we need to solve terrestrial problems. The ultimate value may lie in the humility this knowledge instills. Every revelation about the dark frontier is a lesson in cosmic modesty. We are not the center of the universe. We are a fleeting, conscious glimmer on the edge of an immense and mostly hidden reality. How should this truth guide our actions? Does it render our struggles meaningless, or does it instead charge our brief moment with greater purpose, encouraging us to be better stewards of our world and kinder to one another in the face of the great, dark unknown? The vast, invisible cosmos does not just challenge our instruments, it confronts our deepest beliefs. For millennia, human worldviews were built upon the stage of a small, central Earth, with heavens populated by gods and celestial spirits. Each new revelation about the dark frontier, from dark matter's ghostly grip to an accelerating universe, forces a profound recalibration of our place in the grand scheme. This is not the first time science has reshaped our spiritual landscape. The Copernican revolution was a seismic shock, displacing humanity from the center of creation. Galileo's telescope did not merely reveal moons around Jupiter, It shattered a whole cosmological order built on ancient authority. That shift was violent and deeply unsettling, forcing a painful but necessary expansion of theological understanding. Today's discoveries present a similar, though perhaps subtler, challenge. When we learn that 95% of the cosmos is made of substances alien to our senses, it asks a fundamental question of purpose and design. Does a universe dominated by invisible, seemingly impersonal forces leave room for a divine architect, or does it point toward a reality whose rules are purely physical? The response has been fascinatingly diverse. Some religious traditions see the dark frontier as a testament to God's profound and unknowable majesty, a creation far grander and more mysterious than previously conceived. The awe inspired by a Hubble image of a gravitational lens is not so different from the awe felt in a great cathedral, a humbling sense of a reality vastly greater than oneself. In secular and humanist perspectives, these discoveries forge a different kind of meaning. The understanding that we are stardust woven into the fabric of a hidden cosmic web can instill a deep, ecological connection to the universe itself. Our brief consciousness becomes the universe's way of knowing itself, a fleeting but precious light in the immense dark. This is not a conflict that demands a victor, but a dialogue that enriches both sides. Modern theologians and scientists often speak a common language of wonder, exploring concepts like a multiverse or the fine-tuning of physical constants as points of intersection. The shared ground is the human experience of awe in the face of the unknown. Across cultures, from the meditative spaces of Buddhist monasteries to the analytical halls of research institutes, the cosmic mysteries of dark matter and dark energy evoke a similar primal wonder. They are the modern equivalents of the great myths, stories that help us navigate our relationship with the infinite. So where does this leave your own beliefs? The journey into the dark frontier is not just about collecting data, it is an invitation to reflect. Does the knowledge of an invisible cosmic skeleton make you feel insignificant or more connected to a breathtakingly vast and hidden reality? The answer is deeply personal, a synthesis of data and spirit that each of us must weave for ourselves. This ongoing integration of hard evidence and human meaning is the final, crucial step in our mapmaking, turning cold data into a lived cosmology. A single thread of evidence is fragile, easily dismissed as a coincidence or an error. The true strength of our cosmic map comes from weaving many different threads together into a single, unbreakable cord. Cosmologists do not rely on just the cosmic microwave background, or galaxy surveys, or supernova alone. They combine all of them, creating a multi-pronged attack on the mysteries of the dark frontier. This process is called cross-validation, and it is the bedrock of modern cosmology. Imagine you are a detective trying to solve a complex case. One witness gives you a description. A second provides an alibi. A third offers a motive. Alone, each account might be flawed or incomplete. But when all three stories align perfectly, pointing to the same suspect and the same sequence of events, your case becomes ironclad. This is precisely how scientists build our model of the universe. The cosmic microwave background provides the initial conditions, the blueprint from the infant cosmos. Galaxy redshift surveys map the resulting three-dimensional structure that grew from that blueprint, and distant supernova act as cosmic mile markers, measuring how the expansion rate has changed over billions of years. Each of these probes is independent, each with its own set of potential errors and uncertainties. When they all converge on the same answer, a universe with about 5% normal matter, 27% dark matter, and 68% dark energy, our confidence soars. This is not a guess, it is a consensus built from multiple, independent lines of inquiry. To coordinate this massive effort, projects like the Dark Energy Task Force were established. Their goal was not to build a new telescope but to devise a strategy. They prioritized which methods were most complementary, ensuring that we were not just measuring the same thing in different ways, but truly testing the model from every possible angle. They asked, if dark energy is a cosmological constant, what should we see in the galaxy distribution? What should we measure in the lensing of distant light? By defining these precise, testable predictions, they turned the entire sky into a rigorous laboratory. Yet this beautiful coherence comes with its own profound question. What if the model is wrong in a way that consistently fools all our different methods? What if there is a fundamental flaw in our understanding of gravity or physics that creates the same illusion across every probe we can devise? This is the nagging doubt that keeps cosmologists awake at night. The standard model of cosmology, known as lambda CDM, fits the current data with astonishing precision. But is it the final story, or merely the best fit to a reality that is far stranger? The small but persistent tensions between different measurements, like the Hubble constant disagreement, are the cracks where the light of a deeper truth might finally shine through. Our map of the cosmos is stunningly detailed, yet profound mysteries linger at its edges. The true identity of dark matter remains the most glaring gap. We feel its gravitational hand, but we have never touched a single particle. Decades of searching with increasingly sensitive detectors have yielded only silence, forcing physicists to question their initial assumptions. Was the WIMP hypothesis a decades-long detour? Are we hunting for something far more alien, like actions or an entire hidden sector of dark particles interacting through their own dark forces? Each null result from an underground lab is not a failure, but a signpost closing one path and pointing us toward another, more exotic possibility. Then there is the Hubble tension, a persistent crack in the foundation of our model. Independent measurements of the universe's current expansion rate refuse to agree. One method, using the ancient cosmic microwave background, gives one answer. Another, using supernova and other local markers, gives a slightly faster rate. The discrepancy is small but statistically stubborn, suggesting a flaw in our standard model. Could dark energy be evolving, its strength changing over billions of years? Or does this tension point to entirely new physics, perhaps a new type of neutrino or a feature of the early universe we have not yet imagined? The origin of dark energy is perhaps the most bewildering puzzle of all. The cosmological constant, while fitting the data, presents a theoretical nightmare. When physicists calculate the predicted strength of this vacuum energy using quantum mechanics, the result is a number 1 followed by 120 zeros too large. It is the worst prediction in the history of science, a screaming void in our understanding that hints we are missing something fundamental about the nature of empty space itself. Prominent cosmologists argue that resolving these tensions requires a three-pronged attack. We need bigger, more sensitive telescopes like the Roman and Rubin observatories to deliver pristine data. We need more powerful particle colliders to probe energies where new physics might emerge. And we need bold new theoretical ideas that are willing to challenge Einstein himself. The most exciting breakthroughs will likely come from the intersection of these approaches, when a strange observation in the sky finally meets a revolutionary idea on the chalkboard. This is not a search for incremental knowledge, but for a paradigm shift. What lies beyond our current model of physics? The answer is hidden in the dark, waiting for a curious mind to finally bring it to light. These radical ideas find their home in the mathematics of string theory. It proposes that the fundamental particles of the universe are not tiny dots, but unimaginably small, vibrating loops of energy. A single string, vibrating in different ways, could produce every particle we know, from electrons to quarks. To make the math of these vibrations work, however, string theory requires something extraordinary: extra dimensions of space. We are familiar with the 3 dimensions of length, width, and height plus time. string theory suggests there could be 6 or 7 additional spatial dimensions, all curled up into a size so infinitesimally small that they are completely hidden from our perception. This is where a potential solution to the dark matter mystery emerges. What if dark matter is not a particle in our three-dimensional space at all, but an object or a vibration that exists primarily within these extra dimensions? Its gravitational influence would still leak into our world, explaining its ghostly pull, while the particle itself remains forever out of reach, trapped in a hidden geometric fold of reality. This framework also offers a new perspective on dark energy. The specific way these extra dimensions are curled and stabilized could generate the repulsive pressure that drives cosmic acceleration. String theory attempts the ultimate goal of physics, to unify Einstein's theory of gravity with the quantum mechanics of the very small. In this grand synthesis, dark energy and dark matter are not separate anomalies, but different manifestations of this underlying unified structure. Yet for all its mathematical elegance, string theory remains entirely speculative. It makes no testable predictions with our current technology, living in the realm of profound and beautiful possibility. This leads to an even more expansive concept, the multiverse. If the hidden dimensions of string theory can curl into different stable configurations, each configuration could represent a universe with its own unique laws of physics. In this cosmic landscape, our universe is just one bubble in an infinite froth of universes. We do not live in a universe fine-tuned for life. We simply live in one of the rare bubbles where the random dice roll of physics produced conditions suitable for our existence. In most other universes, the strength of dark energy might be so strong that matter is torn apart before galaxies can form, or so weak that the universe collapses back on itself instantly. This idea potentially solves the fine-tuning problem of dark energy, not by explaining why its value is so small, but by stating that in an infinite multiverse, every possible value will occur somewhere. How could we ever prove such a thing? The collision of two of these cosmic bubbles might leave a scar in the cosmic microwave background, an imprint we could one day detect. The gravitational waves from the Big Bang might carry hints of other universes. For now, these are dreams at the very edge of science. They force us to ask, where is the boundary between physics and philosophy? When a theory becomes so powerful it can describe an infinity of worlds, but so elusive that it cannot be tested in our own, what does that say about our quest for knowledge? This journey into the theoretical abyss reveals a crucial truth, that the most practical applications often emerge from pursuing the most abstract questions. The algorithms designed to untangle the cosmic web are now helping us decipher the human brain. This is the hidden return on our investment in the dark frontier, a cascade of innovation that transforms abstract curiosity into tangible progress. The relentless drive to detect a single, ghostly dark matter particle has pushed detector technology to its absolute limits, leading to sensors of incredible sensitivity. The same superconducting wiring developed for experiments like LUX Zeppelin, which must operate at near absolute zero to hear the faintest whisper of a collision, is now being adapted for ultra-precise medical imaging. Magnetic resonance imaging machines are becoming more powerful and detailed, allowing doctors to pinpoint neurological disorders and tumors with a clarity that was once science fiction. The starlight that guides our cosmic maps finds its way into your pocket. The Charge-Coupled Device, or CCD, was perfected by astronomers desperate to capture every precious photon from the edge of the observable universe. Today, this technology forms the heart of every smartphone camera and digital video recorder, revolutionizing how we communicate, document our lives, and even perform surgery with endoscopic precision. The search for the invisible skeleton of the cosmos demands immense computational power, fueling advances in quantum computing and data processing. The complex codes written to simulate billions of galaxies are now used to model climate change patterns, design new drugs by simulating molecular interactions, and optimize global supply chains. This is not a coincidence. Fundamental science, by its very nature, forces us to solve problems that have never been solved before, creating tools and knowledge that inevitably spill over into our daily lives. The World Wide Web was invented at CERN to help particle physicists share data, a tool that now connects the entire planet. The precise atomic clocks on GPS satellites must be corrected for Einstein's theory of relativity, or your map application would be useless within minutes. When we fund the quest to understand dark energy, we are not just buying a telescope, we are investing in a boundless engine of earthly innovation. Consider the long-term ripple effects. Research into the exotic states of matter predicted by cosmology informs new frontiers in materials science, potentially leading to room temperature superconductors or revolutionary energy storage solutions. The patience and precision required to build a dark matter detector directly improve manufacturing standards for everything from medical implants to satellite components. So the next time you use a precise medical scan or a global communication network, remember that its origins may lie in a scientist's desire to weigh an invisible galaxy. This profound connection between the cosmos and our daily reality underscores why public engagement is so vital. The journey to map the dark frontier is a story that belongs to everyone, for its discoveries, in ways we cannot always predict, ultimately shape the world we all share. The same equations that describe the cosmic web can now be animated on a smartphone screen. This is the power of modern science communication, where complex data from the dark frontier is translated into breathtaking documentaries and engaging podcasts that bring the universe into our living rooms. Filmmakers use visual effects not as mere spectacle, but as a language, transforming the abstract pull of dark matter into a dynamic, flowing river of gravity that guides galaxies into place. Podcast hosts sit down with leading cosmologists, asking the questions we all have, demystifying the hunt for particles we cannot see. Through social media, astronomers share raw, awe-inspiring images from telescopes like James Webb, offering a direct, unfiltered window into the cosmic cartography happening in real time. This work is not a side project, it is a vital bridge. Clear, compelling science communication builds public support for the massive, long-term funding these projects require. More importantly, it inspires the next generation of scientists, engineers, and curious minds. A child who watches a documentary about gravitational lensing might be the one who designs the detector that finally catches dark matter. How can you stay connected to this journey? Follow the social media accounts of major observatories like NASA and the European Space Agency. Subscribe to podcasts that explore physics and astronomy with a sense of wonder. Seek out documentaries that do not shy away from complexity, but make it accessible through stunning visuals and human stories. The greatest discoveries are not meant to be locked away in academic papers, they are a shared human inheritance. As we near the end of our exploration, we are left with a question of our own. What is the most effective way to share these cosmic wonders with our communities, our families, and our children? The answer will determine whether the map of the invisible cosmos remains a specialist's chart or becomes a common treasure for all of humanity. Our journey ends where it began, with a universe of profound illusion. We have traced the outlines of a ghost, mapping a dark skeleton that holds the glittering galaxies in its gravitational grasp. This invisible cosmic web is the true architecture of everything, a scaffolding built from dark matter, upon which the visible universe is merely draped. Yet this skeleton does not exist in isolation. Its story is locked in a cosmic dance with dark energy, the mysterious force accelerating the expansion of space itself. One pulls matter together, weaving structure from the void, while the other pushes it apart, dictating the universe's ultimate fate. Together, these two dark components have orchestrated the entire history of the cosmos, from the first clumps in the primordial glow to the vast, glittering filaments we map today. This understanding did not come from a single genius or a lone telescope, but from a global collaboration of astronomers, physicists, computer scientists, and countless curious minds. It is a testament to what humanity can achieve when we unite in wonder, peering collectively into the dark. The astronomer Carl Sagan once reflected that we are a way for the cosmos to know itself. We are tiny, fleeting beings on a pale blue dot, and yet we have managed to perceive the invisible threads that bind the entirety of existence. This is our greatest inheritance, the relentless curiosity to look into the void and ask what lies beyond the limits of our senses. The map is far from complete, and the greatest discoveries surely await in the darkness. What part of this cosmic mystery resonates most deeply with you? Share your thoughts in the comments below, and subscribe to continue this adventure into the wonders of the universe.